Okay, Assalamualaikum dan selamat sejahtera. So, I will continue lecture for topic 2, part 2. Okay, about industrial distribution equipment. So, this is the outline. And for part 1, I already explained about introduction until switch gear. So, for this part, I will explain about power cable, protection device and MCC. Okay, as we know, this is the main equipment in IPS. Okay. So, for part 2, focusing on power cable and auto control center. Okay. Okay, first we go to power cables. Okay, there are two common types of cables used in IPS. The first one is power cables. Okay. Power cables is used in most of the areas such as feeder, motor load and between switchboard and distribution board. Okay, used for larger size and higher ampacity. Okay, the second one is control cables. Okay, used in various protection and control system. Okay, usually used for small size as well as the ampacity. Okay, this is the structure of power cables. Okay, we can see here, this here is the conductor. Okay, this one the extruder conductor shield. Okay, this one is the insulation. Okay, this one is the insulation shielding. And this one is the concentric neutral. And this one is the cable jacket. Okay, next type of conductor in a cable. There are two types. The first one is solid conductor and second one is stranded conductor. Okay, this is the structure. Okay, this one is for solid conductor. You can see only solid one. And the second one is stranded conductor. There are multiple conductor here. Power cables are classified with respect to insulation as follows. The first one is laminated type. This type of cable use paper, varnish cambric, polypropylene and others. And the types of cable is PILC cables. Okay, and the second one is extruded types. Okay, usually this type use rubber and rubber like compound. Okay, such as PE, SLPE. Okay, okay, this is the extruded types is normally used for cable. Okay, next is the selection of the cable insulation. Okay, there are three types. The first one is 100% level and the clear ground fault within 1 minute. For this level, and then we have 133% levels. Okay, for this level, the clear ground fault within 1 hour, and then for 173% level, okay, the time needed to de-energize this one. The time needed to de-energize the ground fault is indefinite. Okay, so this level is recommended for ungrounded and for resonant grounded system. Okay, there are three main criteria in cable sizing. Okay, the first one is short circuit current. Okay, and then the second one is the continuous current capacity, or we call ampacity, and the third one is starting and running voltage drop in cables. Okay, this is the structure of cables when fault occur. You can see here, and this is how the cable is laid. Okay, this one is how the cable is laid in the industrial. Okay, first we go to power cables, criteria number 1. short circuit current withstand capacity. Okay, for this criteria, okay, the maximum temperature reached under short circuit depends on both magnitude and duration of the short circuit current. Okay, the quantity is equal to I power of 2T, represent the energy input by a fault that acts to heat up the cable conductor. Okay, and then the minimum cable size due to short circuit temperature rise can be measured by using this equation. Okay, equation number 1 here, where A is equal to minimum required cross section area in mm power square, a T duration, and K is the short circuit temperature rise constant. Okay, next the temperature rise constant. Okay, K represent as K is a temperature rise constant. According to this standard, okay, the equation is K, okay, this equation. Okay, this one is for copper conductor. Okay, and this equation K is for aluminium conductor. Okay, the equation is almost the same, but the difference is the coefficient here. This one different with this one, and also this one. So the coefficient is different because the type of the conductor is different. Okay, next we go to boundary condition of initial and final temperature. Okay, we can see from the table here. Okay, this one. There are 3 types. Okay, PVC, butyl rubber, and SLPE/EPR. Okay, the final temperature, this one is for final temperature, and also this is the initial temperature. Okay, we can see here that for SLPE cable, this one, the final temperature and also the initial temperature is much higher compared others insulation. That's why usually for cable we can use only SLPE for good insulation. Okay, here is the common value for K. K is the temperature rise constant. K is given in the table. Okay, the orange color is the conductor. There are 2 types of conductor, copper and aluminium. Okay, this one is the green one is the insulation. Okay, there are 3 types of insulation: PVC, butyl rubber, and SLPE. Okay, and this is all the value of K, temperature rise constant value. Okay, the value of constant K, okay, K value has been determined by using equation number 1. Okay, the value of T is to be determined next. Okay, the short circuit current is varies with time, and the calculation process can be complicated. To simplify the process, the cables can be sized based on the interrupting capability of the circuit breakers or fuse that protect them. Okay, next is the fault clearing time. Okay, we can see here there are 4 types. The first one is for medium voltage system. Okay, use 5 to 8 cycles, and for starter with current limiting fuse, use half cycle, and for low voltage breakers, use 10 cycles, and for low voltage breakers with instantaneous trips, use 1 to 2 cycles. This is the fault clearing time, TC. Okay, we also have to consider a feeder serving large motor which being fed from LV415 or 400 switchgear having a circuit breaker. Okay, this is the minimum fault withstand duration necessary instantaneous setting for cable. Okay, we can see here for relay sensing or pickup time, the time minimum is 20 millisecond, sorry. Tolerance 10 millisecond. Breaker operating time for circuit breaker is 40 millisecond. Relay overshoot 20 millisecond. And lastly, safety margin is 30 millisecond. So the total time for minimum fault withstand duration is 120 millisecond. Okay, so therefore the cable for SLP aluminium selected for the circuit breaker control motor feeder in 415 or 400 switchgear shall be suitable to withstand the maximum rated fault current of 50 km for at least 120 millisecond. Okay, however, okay, an allowance of 40 millisecond, this one 40 millisecond have to be considered due to the aging, okay, frequent number of operation, increase in contact resistance, and also the variation due to manufacturer. Okay, hence the cable selected for a circuit breaker controlled motor feeder in 415 or 400 switchgear shall be suitable to withstand the maximum rated fault of 50 km for at least 120 millisecond plus 40 millisecond, which is equal to 160 millisecond. So we can calculate what is the A, okay, by using the equation number 1 here. So we insert all the value of I, short circuit, and this one is the time value, divided by K. Okay, this one K refer to the K value of SLP aluminium cable, okay, from the given table from the previous slide. So the calculation value is 212.766 mm squared, so that we have to select the next standard cable size, which is much higher from the calculated value. So the suitable size cable is 240 mm squared. So next we go to criteria number 2 for power cables, which is continuous current carrying capacity. Okay, this criteria is applied so that cross section of the cable can carry the required load current continuously at the design ambient temperature and laying condition. Okay, ampacity is defined as the current in ampere that a conductor can carry continuously under the condition of surrounding medium in which the cable are installed. Okay, cable ampacity given as in IEEE 399 section 13 as shown here. This one, this is the cable ampacity. Okay, and we can see here this is the characteristic, the TC, allowable conductor temperature, TA is the ambient temperature, and then delta TD, delta Tin, okay, that one is the temperature rise of conductor, and then RAC is the electrical AC resistance. Okay, R is a resistance. Okay, and then R prime is CA is the effective total thermal resistance of path between conductor and surrounding ambient. Okay, ampacity duration factor is defined as the product of various rating factor which account for the fraction decrease in the ampacity of the conductor. K1 is the variation, this one, variation in ambient air temperature for cable. And then K2 is the cable laying arrangement. Okay, K3 is the depth of laying for cable laid direct in ground. K4 is the variation in thermal resistivity of soil. So the ampacity duration factor K is equal to K1 times with K2 times with K3 times with K4. Okay, first we go to continuous carrying capacity, current carrying capacity K1. Okay, this one. We have 3K, right? K1, K2, K3, K4. First we go to K1, which is for ambient air. Okay, this is the temperature rating factor and also the air temperature. Okay, so we have the temperature for air temperature 20, so the rating factor is 1.81. Okay, rating factor for variation in ground temperature. Okay, there are two types, which ambient air and also in ground. So this one is in ground. So we have the ground temperature and also the rating factor. Okay, next we go to K2. Okay, K2 is referring to cable laying arrangement. So we have two arrangement here. The first one is the arrangement for 25 mm and 300 mm, but the cable is laying separately. This one. Okay, no interconnected by each cable. So there are A here, there are gap here. So arrangement 2, the cable is laid side by side, so there are no gap from each other. So this is the rating factor for multi-core cable laid on open rack in air for arrangement 1. Arrangement 1, there are gaps, right? Okay, so we can see here number of rack 1, so number of cable per rack 1. Okay, so the factor is 1. So is the number rack is 1, and then the cable per rack is 2, so the factor is 0.98. So that is how we read the rating factor for multiple core cable. Okay, this is rating factor for multi-core cable laid on open rack in air for arrangement 2. Okay, so we also have the number of rack and also number of cable per rack here, and also the factor. Okay, so we have to choose what is the number of rack and what is the number of cable per rack. Then we know what is the factor for K2. Okay, next is the rating factor for single core. Okay, this one only for single core cable in 3-foil circuit laid on open rack in air. So there are number of rack and also number of cable per rack and also the factor. So we can choose the factor K2 factor by choosing what is the number of rack and also number of cable per rack. Okay, next is the rating factor for K2 for multi-core cables but laid direct in ground. Okay, previous is in air, but for this table is in ground in horizontal formation. So we can see that this is the spacing. This one is the spacing. Okay, and then also the number of cable in group. Okay, then this is the factor. Okay, this is the K2 for multi-core cables in ground in tier formation. Okay, we can choose the K2 value by knowing what is the spacing and also the number of cable. Okay, next this is the rating factor for grouping of single core cable laid in 3-foil. Okay, laid direct in ground in horizontal formation. So there are spacing here. Okay, and also number of circuit in group and also the factor. Okay, next we go to the K3. Okay, K3 is represent as depth of laying for cables laid direct in ground. Okay, we can know what is the value of K3 after we know what is the cable size and also the depth of laying. Okay, so we can choose the factor by use a suitable cable size, this one, and also the depth of the laying. Okay, then we can know what is the K factor, K3 factor. Okay, lastly, we can know what is the value of K4. Okay, K4 is the variation in thermal resistivity of soil. Okay, this one is for multi-core cables laid direct in ground. Okay, we can know the value of K4 if we know the nominal area of the conductor and also the value of thermal resistivity of soil, and then we can know what is the factor. We can choose the factor by knowing the area and also the thermal resistivity. Okay, this table is for K4, but for 3 single core cable laid direct in the ground, 3 cables in trefoil touching. Okay, so same goes as previous table. We have to know what is the area of the conductor and also the thermal resistivity of soil to determine what is the K4 rating factor. Okay, this is the table for some of the input required and also the source where to find the value. For example, rated, this one for example, rated kilowatt of load. Okay, the source is mechanical process or load list. Okay, for motor data, so motor data sheet by manufacturer and type of cable to be used, this one, number 3. So we can find from project technical specification and so on. Okay, this is the flow, how to know what is the size of cable. Okay, the first step is this one. Okay, we have to calculate the motor current with power factor and the efficiency. Okay, by calculating the motor current, we know what is the rated load current. Okay, the second stage is calculate K value. Okay, by using this equation, K is equal to K1 times with K2. Okay, and then we get the value of ampacity duration factor. Okay, after that, for the third stage, we have to find the cable ampacity value. Okay, this one, from the K value. Okay, K times with cable ampacity, this one. Okay, and then we know what is the cable ampacity. Okay, after we know what is the cable ampacity, we can do analysis. Okay, final step is the analysis, this one. Okay, if I3 is more than I1, that is the analysis. Okay, is the cable size sufficient to serve the load? Okay, these questions can be answered after we know what is the current ampacity. Sorry, cable ampacity. Hence, cable size selected on the basis of continuous current requirement is single run of 3 core times 300 square mm. Okay, this is the size. Okay, this is the types. Okay, aluminium SLPE, ampacity 497. Okay, this one we can take the nearest value from the cable ampacity value. Okay, this is the another example. a motor rated at 160 kilowatt controlled by a circuit breaker fed from main PCC of fault rating 50 km and connected through aluminum XLPE cable requires a cable size of 3 core with size of 240 square mm minimum due to the short circuit rating. Okay, this one 240 is based on the short circuit rating. Okay, however, the next selected size is 3 core with a size of 300 square mm due to the continuous current requirement. So here we can see that two different size with two different requirement. The first one is short circuit rating and the second one is continuous current requirement. So because of different size, so the next consideration will be the voltage drop criteria to choose which is the best size for cable. Okay, next criteria, third criteria for power cable is starting and running voltage drop in cable. Okay, this criteria is applied to make sure that the cross-sectional area of cable is sufficient to keep the voltage drop. Okay, this voltage drop is due to impedance of cable conductor, okay, within the specific limit. Okay, so that the cable can get at least the minimum required voltage at its power supply input terminal during both starting and running condition. Okay, this is to ensure that safe and sufficient operation of the associated equipment at the supply input terminal. Okay, next is the common standard for voltage drop. Okay, we can see here, this is the schematic for three-phase system. You can see here, incoming from the TMB is 11 kV line. Okay, this one, transformer step down to 415, three-phase. And then this one is LV circuit breaker and connect to the controller. Okay, and then from controller to the load, this one is the load. Okay, we can see here, this is the primary feeder. We can see there are 3% voltage drop, and secondary feeder also 3%, and maybe the total for the primary and secondary feeder is about 5%. Okay, so we have to consider what is the voltage drop for that particular line. Okay, next we have to calculate what is the voltage drop. Okay, by using a approximation method. Okay, this one, this is the equation for voltage drop. Okay, this one you already learned in utilization course under voltage drop. Okay, so next is the modified equation for three-phase calculation. Okay, this one is the equation for voltage drop percentage for three-phase calculation. Okay, Vs is equal to voltage supply. So all the value of V, this one is voltage drop value, divided by Vs times with 100, and then we get the value of percentage of voltage drop. Okay, then we go to for calculation that is more accurate. Okay, this one is more accurate equation by considering the horizontal and vertical domains of voltage drop. So this is the equation. Okay, and then N is the number of parallel runs cable. So we have the N number here. Okay. Okay, this is the example, okay, for starting and running voltage drop in cable. Okay, resistance of conductor of 3 core times with size of 300 mm squared for aluminum XLPE cable is equal to 0.128 ohms per kilometer. This is the resistance value. Okay, this one is from manufacturer's catalog. And then the reactance of the conductor for the same cable is 0.071 ohms per kilometer. Okay, and then we have to we know that the length of the cable is 150 m. This one is maybe assume for this calculation 150 m meter. Okay, running power factor of the motor is 0.85. Okay, this one is standard power factor. And then starting motor power factor is 0.3. Okay, this one is for starting motor. Okay, and then starting current of motor is 6 times rated current. Okay, this one is the starting current. So 6 times from the rated current. Okay, assuming a voltage drop of 1.5% in the cable for incoming feeder, that is from source to power control center. Okay, from the information given for that cable, so there are some questions that can be asked. Okay, the first one is maybe what is the running voltage drop from the PCC to load. Okay, and then what is the total running voltage drop from source to the load. Okay, and then what is the starting voltage drop, okay, from PCC to load. And also lastly, what is the total starting voltage drop from source to the load. Okay, this is some questions that can be asked to find what is the voltage drop in the cables. Okay, next is the last subtopic, protective device. Okay, the circuit breaker is a device that ensures the control and protection on a network. Okay, it is capable of making, withstanding and interrupting operating currents as well as short circuit currents. Okay, the main circuit must be able to withstand without damage of, the first one is the thermal stress caused by the short circuit current during 1 or 3 seconds. And then from the electrodynamic stress, this one caused by the peak of short circuit current. Okay, peak of 2.5 times of I short circuit for 50 Hz. Okay, standard time constant of 45 millisecond. For 2.6 times I short circuit for 60 Hz, standard time constant is also 45 millisecond. And for 2.7 times I short circuit, okay, for longer time constant. And lastly is constant load current. So these three damage must be considered for circuit breaker analysis. Okay, next is the characteristic of a circuit breaker. Okay, the first one is rated operational voltage, VE. Okay, this is the voltage at which the circuit breaker has been designed to operate. Okay, the second one is rated current, I in. Okay, maximum value of current that a circuit breaker can carry indefinitely at a specific ambient temperature. Okay, that is rated current. Okay, next is overload relay trip current or short circuit relay trip current, IR. Okay, this is the maximum current that the circuit breaker can carry without tripping. Okay, value that trip the circuit breaker repeatedly on the occurrence of high values of fault current. Okay, lastly is the rated short circuit breaking capacity, IM. Okay, this is the highest prospective value of current that the CB is capable of breaking without being damaged. Okay, this is the tripping current range of overload and short circuit protective device for LVCB. We can see here there are some breakers, circuit breakers, different types. This one, different types, thermomagnetic and electronic types, and this is the overload protection, okay, setting, and this one is for short circuit protection setting. Okay. Okay, next is the circuit breaker versus fuse. We can see here, this is the graph for the operation. Okay, here is the normal load current condition, and this is the point of fault. Okay, when fault occur, the fuse will open within 1/4 to half cycle. Okay, and then we can see that the current go to the peak value. Okay, this one is the peak value of the current when fault occur. And then we can see here that the circuit breaker will operate here, and it takes more time to operate compared to fuse. Okay, and we can see here this is the heat energy because of the fault. Okay, this is the performance curve of a CB. We can see here this one. Okay, this red color is the overload. Okay, overload protection, and then we have yellow, right? Yellow one. This one is for short circuit instantaneous protection. Okay, this is the setting. We can see that for overload setting IR here. Okay, this is the overload. Okay, this one is for overload, and then this one is IM for short circuit trip current setting. This one, and then we have short circuit instantaneous relay. This one. Okay, and then this one is breaking capacity. Okay, this is the close open cycle of CB. Okay, you can see here. Okay, first when fault occur, okay, fault occur here, and then relay will pick up. Okay, this time relay will pick up the fault condition, and then the trip coil energized. Okay, this one. Okay, this one is the trip coil of the circuit breaker will energize, and circuit breaker will open, will operate. And then circuit breaker opening time, there are some delay here for opening time, and also for circuit breaker arcing. And this one is the condition of open. Okay, open, circuit breaker open. Okay, means that circuit breaker will isolate the incoming supply from the load. And then here is the fault extinguish. Okay, here. Okay, after the circuit breaker open, and then the relay will reset back to its setting. Okay, this is the total fault curing time. Okay, from the fault occur here to the fault extinguish. Okay, this is the CB operating time. Okay, this is the from open position to close position of CB. Okay, we can see here. Okay, this is the energizing of closing circuit. Okay, this one is for open position of circuit breaker, and then contact touch in the first closing pole. This one. Okay, contact and start of current flow in the first pole when the contact touch the first closing pole, and then contact touch in all poles here, and the circuit breaker start to close. Okay, this one is the close position, close open time. Okay, this one current will flow when the circuit breaker is in close position. Okay, and then here is the separation arcing contact in all poles, and finally we can find that arcing extinction in all poles, and then contact movement here. Okay, Okay, this is the automatic reclosing cycle. Okay, the first one is this one is the close position. Again, we can see here, and this one is the open position of the CB, and come back to the close position. Okay, so means that in close position there are current flow, and then when there are fault occur, so the circuit breaker will open. Okay, this one is the open position of the circuit breaker when the fault occur, and then when the fault occur and recovery automatically, so that the current, the circuit breaker will close, will automatically reclosing cycle happen here, and the current flow again. Okay, last subtopic is the motor control center here. Okay, for part 2. Okay, this is the diagram of motor control center. Okay, we can see here MCC, motor control center. Okay, from the panel board, switchboard, this one, switchboard to the motor. Okay, this one is from utility. Okay, okay, and then connect to the feeder bus away to the switchboard, this one. Okay, this one switchboard. Okay, connected from the outdoor feeder bus away here, and then connect to feeder bus away here to the panel board. Okay, this one is panel board, and then going to transformer, this one for VAC 480, and then connect to the 120 VAC panel board, this one, and from the panel board will connect to the socket, and also for lighting. And then here from the switchboard directly connect to the motor control center, and then from the motor control center going to the motor, this one for each motor. Okay, this is the diagram of the motor operation. We can see here, this one is the live. Okay, live supply, this one is supply, and then we have start push button, this one. Okay, this one for circuit breaker, and then we have to push button to start the operation, and then this is the motor starter. Okay, this one, and this is the overload relay. Okay, for protection, and then this is the operation of the motor. Okay, okay, this is the singular diagram of the operation. Okay, typically one motor starter controls one motor only. Okay, when only a few geographically dispersed AC motors are used, the circuit protection and control components may be located in a panel near the motor. This one is the motor starter, you can see here. Okay, this one, and this one is for short circuit protection. Okay, this one is for disconnect. Okay, this is the MCC center. Okay, this is the layout. Okay, layout of simply physical grouping of combination starter in one assembly. Okay, we can see here, this is the MCC. Will control all the motor here. Okay, in one room. Okay, okay, I think that's all for topic 2 part 2. Okay, almost all the theory, and we will continue in part 3 for example and calculation. Okay, is that? Thank you.